Hello and welcome to my third video. This is on the algebra of modulo and sum and product functions. This is not the logical sum and the logical product, which would be maximum of and minimum of functions. This is modulo sum and product functions. So I'll start with the definition of A. Let A equal a number in a base system. Example, base 2, binary. A can assume the value 0 and 1. Base 3, ternary. A can assume the value 0, 1 and 2. Base 4, quaternary. A can assume the value of A 0, 1, 2 and 3. Base 5, quinary. A can assume the value A equals 0, 1, 2, 3 or 4. So an equals a 1 if and only if A equals n and a 0 otherwise. So here's an example of A, 0 and A1. A is a 0 there, so it's a 1 there and a 0 everywhere else. A1, A is a 1 there, so it's a 1 there and a 0 everywhere else. So we'll look for the equation for A0 using Fermat's-Subtle theorem. A to the power p minus 1 equals 1 modulo p. Now modulo is a remainder when the base, i.e. the modulus p, is divided by a number. So 4 divided by 3, if p was equal to 3, would go once with remainder 1. So 4 divided by 3 modulo p, modulo 3 is 1. It's the remainder. So a to the p minus 1 equals 1 mod p, where p is prime and a is not divisible by p. So using this result here, I have a here is 0 to p minus 1. A to the power p minus 1, 0 is obviously 0. So we have a 1 everywhere else. Times it by p minus 1, get p minus 1 there and 0 there. And we add 1, so we get 1 there, and 1 to p minus 1 is p, which is 0 modulo p. So A0 is p minus 1 times a to the power p minus 1 plus 1 for any prime base. Prime number is any number that can only be divided by itself or 1 to equal a whole number. So 4, for example, would be quaternary, wouldn't be prime because it's 2 times 2. This is a matrix representation of A0 and A1. Here we have A0 is A plus 1 and A1 equals A. So we represent that in a matrix form. Here we have the coefficients of A to the power 1 and A to the power 0. A to the power 0 is 1. A0 and A1 here. So we have A0 equals A plus 1 and A1 equals A plus nothing times 1, which is A there. So the binary coefficients of CA to the n, the powers of n, so powers of A, from this 2 by 2 matrix, from this matrix, we have CA to the 0 equals 1, and CA to the 0 equals A plus 1, which is there. CA to the 0 is A plus 1. Here we have the binary Reed Muller expansion. This is how you synthesize the function f for a binary system. You have the variables a and b. This is for 2 variables. You could have more, just 1, 2, 3, or any amount of variables. This is a system for 2 variables a and b. And k3, k2, k1 and k0 are constants. They're just numbers. Now you have the coefficient k3 of a and b. K2 is a coefficient of b, K1 is a coefficient of a, and K0 is the constant, which is a to the 0, b to the 0, which is 1 times 1, which equals 1, times Ko, which equals Ko. Now these are constants, these are Reed Muller coefficients, and are constants, just numbers. So I'm going to introduce the variable s here, We have S3, S2, S1 and S0, and that is f times the coefficient of a to the 1 and b to the 1, which is f times 1 times 1, which is f. Similarly, S2 is ca to the 0, cb to the 1, which is a plus 1 times 1, which is f, times by f, which is f times a plus 1. ca to the 1, cb to the 0, which is f times 1 times b plus 1, which is f times b plus 1. And f times ca to 0, cb to 0 is f times a plus 1 times b plus 1. Sn is a variable. Here we have the proof. F equals f times a1 plus a0 times b1 plus b0. Now a1 plus a0 equals 1 and b1 plus b0 equals 1. So we have f times 1, which equals f. So if expand out the brackets, we get that. And we substitute in the values of a1, a0, b1 and b0 here. So a1, b1 goes to a and b. a0 is a plus 1, b1 is b. a1 is a, b0 is b plus 1. And a0, b0 is a plus 1, b plus 1. So we have the function is s3 times ab plus s2b plus s1a plus s0. So kn is the sum of Sn over the range of f. Now the range of f here, I've got an example of f here. The range of f is the number of rows that the column takes up. So the range of f here will be 4 because there's 4 rows. Here we have an example of f with the truth variables a and b here listed in a truth table. A follows a pattern 0, 1, 0, 1. B follows a pattern 0, 0, 1, 1. And we have a0. We have all these constants here. So there are 1 there and a 0 everywhere else. Here I have a worked example. We have a, b, b plus 1, a plus 1 and f, s3, s2, s1, s0. Now s3 is just f, and you k3, k2, k1, k0 are the sum of the columns of s1, s2, s3 and s0. So this would be k3, this would be k2, this would be k1, this would be k0. So s3 is just f, which summed together 1 plus 1 is 2 is 0. s2 is a plus 1 times f, which is 1 there, and the sum of that is 1. s1 would be b plus 1 times f, which is a 1 there and a 0 everywhere else, and the sum of that is 1. And s0 is a plus 1 times b plus 1, which would only give a 1 there, but f is a 0 there, so the whole column is a 0. Now k2 is the coefficient of b, k1 is the coefficient of a, so you have the function f equals a plus b. Here we have the matrix representation of a ternary system of a0, a1 and a2. Now a0 is 2a squared plus 1, a1 is 2a squared plus 2a, and a2 is 2a squared plus a. Now, these can be represented in a matrix with a squared, a and a to the 0 there, a0, a1 and a2 there, and we have a0 equals 2a squared plus 1, a1 is 2a squared plus 2a, a2 is 2a squared plus a2 there. So from this matrix here, the coefficients of ca to the n from the 3 by 3 matrix, ca squared equals 2, ca to the 1 equals 2a, you have 2 times 0, 2 times 1 is 2, 2 times 2 is 4, which is 1 modulo 3, and CA0 here is equal to A0, which is 2a squared plus 1. So CA squared is 2, CA1 is 2a, and CA to the 0 is 2a squared plus 1. Here we have the ternary Reed Muller expansion. This is for two variables, and basically it's the product of all the powers of a and b multiplied together. K again are ternary Reed Muller coefficients, and they're constants, they're just numbers, and f is synthesized by the various constants of the expansion. Well, it would be a polynomial, but it's for two variables. Now f equals s8 a squared b squared, s7 a squared b, s6. S is the same as before with the binary system. You have S8 to S0. And in the binary case, as in the binary case, Kn is the sum of Sn over the range of f. In this case, the range of f would be 9 columns of the truth table. So here we have S8 to S0. Sn is a variable, and f, as in the binary case, it's f times the coefficient of a to the n times the coefficient of b to the n. So a squared b squared is f times 2, which is f. 2 times 2 is 1 modulo 3. And here we have the various coefficients. Ca to the 0, cb to the 0 is f times 2s squared plus 1 plus 2b squared plus 1. Sn is a variable. Here's the proof again. So following the binary routine, we have f equals f times a2 times a1 times plus a0 times b2 plus b1 plus b0. Now this is equal to 1, and so is this. So that equals 1, f times 1, which equals f. And we plug in the values of a2, a1 and 0 here. That's a2, that's a1, that's a0. And b2 here, b2, b1, b0. And what we're going to do is we're going to cancel the 2a, a and 2a there, that makes 3a, which is 0a, and 2b plus b, which is 3b, which is 0b modulo 3. And we're going to leave that as it is and split the a into two lots of a there for the a squared, and leave 2a squared 1 plus 1 as it is. Same for b. And if we multiply this bracket by this bracket, we get f times a squared times b squared. That's a squared b squared there. 2 times 2 is 1 times f. And we get the various coefficients of a to the n, b to the m here. So the coefficient of s would be, that would be s0 would be f 2a squared plus 1, 2b plus squared plus 1. Here we have a worked example. This is f, this is a, and this is b. There wasn't enough room to fit all the variable functions of a and b in, so I'll just say that this is the function f. This is s0, s8 is the function f, which in this case is here is the a plus b modulo 3, and s0 is 2a squared plus 1 plus 2 times 2b squared plus 1, which would be a 1 there and a 0 everywhere else, times by f. F is a 0 there, so it's a 0 everywhere else. This would be K8, K7, K6, K5, K4, K3, K2, K1, K0. It's the sum of all the columns of Sn. And from here, K8 is 0, K7 is 0, K3 is 0, K5 is 0, K4 is 0, K3 is 1, K2 is 0, K1 is 1, and K0 is 0. Now K3 is the coefficient of B, and K1 is the coefficient of A. So F equals A plus B. So we're going to have a brief look at the quinary and quaternary systems. Modulo 5 quinary and Modulo 4 quaternary. Now the Quinary Reed Muller expansion is all the coefficients of a to the n times b to the n. This is for two variables, a and b. And we have a to the 4, a to the 3, a to the 2, a to the a to the 0, b to the 4, b to the 3, b to the 2, b to the 1, b to the 0. The coefficients k are constants, they're just numbers, and as in the binary and ternary case, you would have s, 24, s, 23, s, 22 for example, which would be the sum. K would be the sum of s over the range of f. In each case, the range of f for this would be 25. So the quinary coefficients of Ca to the n, Ca to the 4 is 4, Ca to the 3 is 4a, Ca to the squared is 4a squared, Ca to the 1 is 4a cubed, and Ca to the 0 is 4a squared plus 1. For a quaternary system, quaternary isn't prime, so a0 cannot be derived by algebraic means. So what you do is you let f equals 0 when any of the inputs equal logic 4, and you use a quinary system. You use a quinary system where f equals 0 when any of the inputs equal 4, and thus the logic 4s can be omitted from the truth table, although one or more of the Reed Muller coefficients may be 4, and all calculations are done modulo 5. So it's just like a fiddle. I mean, you could use the quinary system for equally well ternary or binary, but it would be very inefficient. This is just a dodge. Here we have the general proofs. Now a to the n is p minus 1, a plus p minus 1 times n to the power p minus 1 plus 1. If a equals 0, you get p minus 1 a to the p minus 1 plus 1, which is A's equation for a0. Now the binomial coefficients of Cp and C to the p minus 1r is p minus 1 times p minus 2 times p minus r over r factorial. So that modulo p, although all the powers of p equate to 0, and you're left with minus 1 times minus 2 times minus r, which is plus or minus r factorial. So c to the p minus 1r equals minus 1 to the power r mod p. Because you've got a factorial divided r factorial divided by r factorial, but this may be plus if these terms are even, and minus if these terms are odd, if r is odd. So that's where the power r comes in. So r to the 0 is 1, which doesn't take into account this formula. So a to the power a minus n to the power p minus 1 is minus 1 to the r, coefficient of cp minus 1r, times a to the p minus 1 minus r, times minus n to the r, modulo p. Now these cancel each other out, so we're left with a minus n to the p minus 1 equals the sum of between r equals 0 and p minus 1, a to the p minus 1 minus r times n to the r mod p. Now we have minus 1 is p minus 1 mod p, therefore an equals 1 plus p minus 1 times the sum of r between r equals 0 and p minus 1, a to the p minus 1 minus r times n to the r mod p. So if you let a equal n, a to the n equals 1 if a equals n and 0 otherwise, so we have 1 equals 1 plus p minus 1, and n is being replaced by r there, so you have the sum of r equals 0 and p minus 1, a to the p minus 1 minus r times a to the r mod p. Therefore the coefficient of c x to the n, where x could be equal to a, b, c or d, or any variable name, equals p minus 1 x to the p minus 1 minus n. So I've called Rn here. And c to the 0 is p minus 1 x to the p minus 1 plus 1. If this is 0, r equals 0, you have p minus 1 times a to the p minus 1 minus r plus 1 here. So this is what this is about when r equals 0. Anything to the power 0 equals 1. Right. Here we have the matrix representation of a to the n. These are the coefficients of a to the power p minus 1, p minus 2, and a to the powers. Az, if z is p minus 1, that's a to the p minus 1, that's a to the p minus 2, and that's a to the 0 is 1. And all this is equal to 1. And I can tell you this is what this equation is about here. 1 equals 1 plus all that. So here we have two matrices, one row and one column, and that's equal to 1. Now 1 is the identity matrix. So what I'm suggesting is these are the inverse of each other. Now to be an inverse it's got to be a square matrix. And so, but we can make these square matrices by expanding A here, and expanding here, A here. So if we take this matrix and expand A from 0 to p minus 1, we get this square matrix here. We have p terms here and p values of A in that direction. So we have a square matrix here. That is there, that column's there, and that equals A0, A1 all the way down to AZ, AP minus 1. If we expand this column in the A direction, in that direction, from 0 to 1, we have this, which is a square matrix. This is A equals 0, A equals 1, blah blah blah, equals P minus 1. And we have 0 there and a 1 everywhere else for A to P minus 1, because it's AP minus 1 to the n equals 1. And we have 1 there, which is a 1 everywhere else. If we expand A0, A1 and AZ, we get the identity matrix E, which is a 1 on the diagonals and a 0 everywhere else. So because we've got the identity matrix there, this has to be inverse of this. So that's proved the result. Well, that didn't make any sense. This is an example using a ternary system. This is A and this is the inverse of A. This is 0, A squared here with 0, 1 and 2. A squared, 2 squared is 1. This is A, 0, 1, 2 and this is 1. These are the coefficients of A squared, A and A to the 0 here. And all calculations are done modulo 3. So, for example, this is the dot product of the two matrices, which equals the identity matrices, and we have 2 times 0 plus 0 times 0 plus 1 times 1, which equals 1. There's a 1 there. And here we have this row position here will be this column times this row, which is 1 times 2 plus 1 times 0 plus 1 times 1, which equals 3, which equals 0 modulo 3. So if you do that for all the various dot products, rows and columns, you get the identity matrix. Therefore, we have A here, A to the minus 1, the inverse of A here, equals E, the identity matrix. So we have, take the transform, now the transform T, transform takes the rows and turns them into columns. So it's an inversion about the diagonal. So you take the row, that row will be that column, that row will be that column, and that row will be that column. So the transform of that will be e to the t. The identity matrix is transformed, which equals the identity matrix, because if you flip it around it's the same matrix. So we have a to the minus 1 to the t is dot product a to the t equals the identity matrix. Now, A transform times K equals F. K is the constants of the Reed Muller expansion, and F is the function you're synthesizing in matrix form. So A to the t times A to the minus 1 to the t times K equals A to the minus 1 TF. That cancels to E, and you're left with A inverse transformed times F. So that's the inverse of A transformed times F equals K. Here we have an example in the binary and the ternary case. This is K, these are the coefficient, these are the Reed Muller coefficients in the binary case. These are Reed Muller coefficients in the ternary case, binary, ternary. These are F, I've labelled them F0 and F1, F0, F1 and F2. This is just in response to 0, 1, 2 for A. And here we can see that F0 is equal to K0 there, and K2 plus K1 plus 0 there, and K1 plus 2K1, 2. K2 plus 2K1 plus K0 for F2. Right. And the inverse transformed times F times the function equals K, these Reed Muller coefficients, which are constants. And here we have F0 equals 2 times F there, 2A times F there, and A plus 2A squared plus 1F times F there. In each case, these were taken from the coefficient matrices of A to the power 2, 1 or 0. Now all this is fine until you have to deal with two variables. That's fine for one variable, but what happens when you've got two variables or more than two variables? So here we have the Konica product. The Konica product is a matrices operation, but it's different to the dot product which we saw earlier. The Konica product takes two matrices of any size and multiplies them together in such a fashion that you get B there and 1 there. So two matrices here, A and B. B times A minus 1 there, and 1 times A plus 1 there, A and 1 there. If you expand that out and multiply them together, you get A and B there, A there, and 1 there. Here's an example. I'm multiplying two square brackets the same, which is to a power, the Konica power of 2 squared, and you take this matrices and display it there, and you multiply it by the coefficients of each of the other matrices there. Coefficients. So you get 0 there for those 4, that pattern there for those 4, that pattern there for those 4, and that pattern there for those 4. So if A is a square matrix of order m to the power n, where m is a prime base and it has to be prime, and n is the number of variables, it is now shown that m to the n times the inverse times m to the n equals the identity matrix of m to the n. Now this subscript m to the n just represents the size of the square matrix. So if m equals 3 and n equals 2, you'd end up with a 9 by 9 matrix. Here we have a proof. This is a relationship between the dot product and the Konica product, and that is the dot product times by the Konica product times by the dot product. So first we're going to assume the dot product of the Konica product powers can be collected there. So it's A dot B to the Konica power. So letting n equal 1, we have A dot B equals A dot B, and from 1 we're substituting in A and A to the power n for B, B and B to the power n for C and D, and that equals A dot B times the Konica product of A to the power Konica power n times B to the Konica power n. So A to the power A to the Konica product of A to the Konica power n is dot product B to the Konica product of B to the Konica product n equals AB times A dot B to the power n, or the Konica power n. Therefore, by induction, A to the Konica power n plus 1 dot B to the power Konica power n plus 1 equals A dot B to the Konica power n plus 1. So by induction, this holds. Next we assume that we can the inverse to the power, the matrices of A and its inverse and the identity matrix are equal all to the power, Konica power of n. So from 3 and letting n equal 1, we have that, which has got to be true, because the dot matrix of two square matrices of order m has to equal a matrices of order m, which is E. So from 3, we have that. Using 2, we group the powers together, and we multiply by a to the m and its inverse to the m on both sides. Then we have that to the power n plus 1, because we multiply it by that, so that adds 1 to the power. That equals e to the times e to the power n has got to equal n plus 1 there. So we have that equals n plus 1. And then we split the powers there. So we have a to the Konica power n plus 1 plus the inverse power Konica power n plus 1 equals the identity matrix to the Konica power n plus 1. Therefore, by induction, this works. Now we're going to look at this equation again, and we're going to let A equal the identity and B equal that to the power n, and AM and C and D equals A and A to the power n. So we have, on this side of the equation, we have this e to the power e to the m, e to the power m to the n, and on this side we have a to the m, Konica Product a to the power n to the m. So anything with the identity matrix, dot product of a equals a, and the same here, that equals a, and we're left with the Konica Product of em to the n, and am, Konica Product am to the n. Now these sides are equal, so this has to equal the identity matrix, and it has to be to the n plus 1, because the powers add together. So that the Konica Product of am times a to the mn equals a em to the n plus 1 times the Konica Product of am times am to the n. Therefore, this has to be the case. This has to be an identity matrix. So we assume, nearly there, em to the Konica power n equals em to the n. From 6 and letting n equal 1, we have that. So em to the n, Konica power n equals em to the n. And we have times both sides by em, and using 5, em to the n plus 1 is em to the n plus 1, which is using that result there. So therefore, by induction, em to the n equals em to the power n, or em to the Konica power n equals em to the n. So from 3, we have this equation. Using 2, we combine the powers and let that equal that. And we say that the square matrix of order m, the dot product of two square matrices of order m, has to be the dot product of a matrix to the order m, which equals that. Then you can e to the m, em to the Konica power n equals that. This is equal to e. This is equal to e to the m, so that's got to be the same operation. That's got to be the dot product of the inverse times a times a inverse to the m to the power n. Therefore, the inverse and its matrices is equal to the identity matrix for any matrix of order m or any power n. Therefore, you can say a to the m to the Konica power n is a to m to the power n. So, what does this mean? Well, let K and F be 1 m to the power n by 1 matrices, and let a to the m to the n transformed times km to the n equal fm to the n. Now a, k and f, k is the Reed Muller coefficients and f is the function. So they're 1 by mn column, 1 column functions for a matrix. So if you times it by its inverse transformed, you get that. Times both sides by the inverse of the matrix transformed. And you can group them together under one transform. And that has to equal the identity matrix transformed. And we have the same here, times f. So that equals e to m to the n transformed has got to be e to m to the n. So I have that, and we get the inverse of the matrix A transformed equals the function f times dot product times the function f equals the Reed Muller coefficients K, the matrix K. So, what does that mean? Well, it means, from the two worked examples I showed you before, this is 1, this is a plus 1, this is b, and this is a plus 1 times b plus 1. In the order of the truth table, starting from the top of the truth table on the left to the bottom of the truth table on the right. So if you can imagine that on its side, that would be the truth table. Here's the function f, which is before is the a plus b, and here are the Reed Muller coefficients, which are constants. So what it shows is that when this has to be the sum of the columns of the coefficients of a and b to the n. So this would be S4 here. Yeah. S4, S3, S2, S1. This will be F0, F1, F2, S3. This will be K0, K3, K4, K3, K2, K1, K0. And the same deal here. This is for the ternary example. Here we have 1. Here we have A. Starting from the top of the truth table on the left to the bottom of the truth table on the right. A. This is B. This will be A times B. And this would be 2A squared plus 1 times 2B squared plus 1 here. This is F. Starting F0 here. And K3, K8 there, K8 to K0 there, and this would be S8 there, S7, S6, all the way down to S0 here. So that concludes the proof. It's a bit long-winded and a bit technical, but I hope you enjoyed it. Thanks for watching. Bye.